Hello everyone, and welcome back to the second part of the two's complement binary systems tutorial. So in this part we're going to cover overflow and something that I call length determination. So let's start. So to talk about overflow, we need first to talk about binary addition rules. Binary addition rules. So here are the rules. So if we add 0 plus 0, this is supposed to be 0. And if we add 0 plus 1, this is supposed to be 1. And if we add 1 plus 0, that is supposed to be 1. And if we add 1 plus 1, that is supposed to be 0. And you carry the 1 to the following bit. So it's essential that we understand these rules before we move on to talk about overflow. Let's get back to the two's complement binary representation. Now, if we have, let's move this a little bit up. Okay. If we have an n bits, if we have two n bits, two's complement if we have two bits, if we have two n bits two's complement numbers with the same magnitudes but different signs or opposite signs, and we add them up, the result is supposed to be 0. What I'm trying to say is, if we add -5 and +5 in an n bits two's complement binary representation, we are supposed to get 0. So let's put this assumption to test. Okay, so here, if I add +5, okay, so that's +5, and -5, I am supposed to get 0, because here, this is +5 right here, and this is -5, and this is -5. If you don't know how to arrive at these values, please watch my previous tutorial, and because it shows you how to do that. So let's add them up. According to the previous rules, 1 plus 1 equals. Now, before I start, since the number of bits that we're using here, we are using a 4 bits two's complement binary system. Okay, 4 bits. That means any value beyond these 4 bits does not count. Why? Because we're using a 4 bits two's complement binary system. So let's add up these values, okay? And these are the weights here. So 1 plus 1 equals 0, carry 1. 1 plus 1 equals 0, carry 1. 1 plus 1 equals 0, carry 1. And 1 plus 1 equals 0 here, carry 1? Yes. But again, since we're using 4 bits two's complement binary system, so anything beyond these 4 bits does not count. So we just proved that if you add two numbers with the same magnitude but different signs, the result would be 0. And that's the beauty of the two's complement binary system. Now, there is one point that we need to bear in mind when we are doing this, when you are using two's complement to add numbers. And let's drag this up a little bit. And this point, I'm going to write it down, states that an overflow occurs, an overflow happens or occurs when the result when the result exceeds the limit of representation. Okay, so what does that mean? So an overflow happens or occurs when the result exceeds the limit of representation. What do I mean by that? Let me illustrate. If we are using a 4 bits, let's say that we are using a 4 bits 2's complement binary system, right? Complement binary system. So if you remember when we talked about range, this 4 bits 2's complement binary system is capable of representing numbers ranging from -8 to +7, and we covered that in the previous part of this tutorial. So if I add two numbers and the result of addition exceeds the limit of representation, which is in this case 7, then an error will occur. Same thing if I add two negative numbers in a 4 bits to its complement binary system and the result is smaller than -8, an error occurs. So am I telling you that if 2, 4, 8, if I add 5 plus 5, sorry, it's -5, 5 plus 5 in a 4 bits binary, in a 4 bits to its complement binary system, the result will be an error? Of course, because 5 plus 5 equals 10 and 4 bits can only represent up to 7. So let's put this to test. 1 plus 1 equals 0, carry 1. 1 plus 0 and 0, so we have 1 here. 1 plus 1 equals 0, carry 1, and the 1 would be here. Okay, so what do we got here? Well, actually, according to the 2's complement binary notation, this number here equals, remember, the most significant bit is negative. So this is -8 plus 2. This here actually is -6. This is an error. Why? Because the result exceeds the limit of representation. Now, there's an easy way that you can know if there is an overflow occurred. You just need to look at the most significant bits, and if the sign of the result is different from the sign of the two numbers that were added, then there's an overflow. See here, the sign is positive because most significant bit is 0. Sign is negative here because the most significant bit is 1. So, and as a rule of thumb, let's write this down before we forget it, actually, right? So overflow, and overflow occurs or happens only when you add numbers with the same sign. With same sign. It's very important that you know that. If you're adding numbers with different signs, overflow will never occur. And you know that it happened, so overflow occurs only when you add numbers with the same sign. And you know it happens when the result has a different sign. How do you know that the result has a different sign? Very easy. If the two numbers have zeros in the most significant bit, watch out for the most significant bit in the result. If it's got 1, well, that's an overflow. Same thing, I'm going to very quickly take a negative example. If I add 2 minus 5s together, it's supposed to be the result should be -10, which exceeds the limit of representation, and that means an overflow. So let me move this a little bit. So here's -5, right? Because this is 1 2. Oops. This is 1, 2. I don't know why it keeps doing this. This is 2, this is 4, and this is minus 8. Remember? So 2 minus 5 together. 1 plus 1 equals 0. Carry 1. 1 plus 1 equals 0. Carry 1 plus 1 is 1. Carry 1 here. And 1 plus 1 equals 0. Carry 1. Since it's 4 bits to its complement binary notation, binary system, this does not count. So again here, instead of having minus 10, we are actually having 4 plus 2. This equals 6, positive 6. So this is an error, right? And again, you can detect it by saying, okay, we have 2 negative numbers, and the result is positive. So that's how you tell if there is an overflow. Okay, so we've covered this point. So we are done with talking about overflow. This is going to take us to our last point, which is length determination. And to talk about length determination, we're going to very quickly cover a mathematical function. There is a function in math, right, that is called the ceiling. And it looks like this. If you have a number, x, so the ceiling of x looks like this. This is how you express it. See the ceiling, right? It's 2 brackets, and it's got this, dash only in the upper part of the bracket. Now, the ceiling in mathematics of a number is defined as the smallest integer, okay, the smallest integer that is greater than or equal to x. Okay, let's take an example. So the ceiling of 4.5, or no, let's say 4.1. Ceiling of 4.1, the smallest integer that is greater than or equal to 4.1 is 5. You need an integer, 5. Okay, the ceiling is 4.9, is 5. Okay? Okay. Now, we needed to get this out of the way because we're going to use it. So, this is the ceiling function. What does this have to do with length determination? If I tell you, I need you to represent number 5 in a 2's complement binary notation, but I'm not going to tell you how many digits you're supposed to use. So there is a way that you can figure out how many digits, or that you determine the length of this 2's complement binary notation if I didn't tell you. Now, you might ask, why do I need to determine the length? I'm going to tell you in a couple of minutes. And it will be especially, or you know what, let me tell you now. If I asked you, here's an exam question, would adding 132 and, if you had a number 132 and 56 together in 2's complement, if you add these numbers in 2's complement binary notation, will that result in an overflow? Will that result in an overflow? This might be an exam question, so I'm simply asking you, will adding 132 and 56 in 2's complement binary notation result in an overflow? The normal way that you do this is you represent this, and then you represent this, and you add them up. If the result has an opposite sign, that's an overflow. But there's an easier way. If you can figure out how many bits 132 needs, right, and then you add them up decimally, right, like you say, let's use the calculator here. Calc. If you say 132 plus what was it? 56. Yeah, that's 188. So if you add them up decimally, and all you can do, and you can actually determine how many bits are needed to represent this, right? And how many bits are needed to represent this, and you can just compare. If they're the same, that's fine, so there is no overflow. But if this number needs more bits than the biggest of the two needs, that means there's an overflow. Okay, so that will take us, if I give you a number, how do I determine the number of digits or the number of bits that is needed to represent it in two complements binary notation? You use this equation. N, or the number of bits, equals the ceiling of log base 2 x plus 1 plus 1. Now, don't be scared. I'm going to explain that. Let's drag this up a little bit. That is if x is a positive number. If x is a negative number, then the equation that you need to do is the ceiling of log base 2, the absolute value of x plus 1. Again, that is if x is negative, use this equation. If x is positive, use this equation. Now don't be scared, because we're going to take an example that's going to make things clear. Here's a question. If I asked you, what is the minimum number of bits that is required to represent 5 in a 2's complement binary notation? So use this equation. That would be the ceiling of log base 2, x is 5 plus 1 of 6 plus 1. There are websites that can make you get this value, or use your calculator, use a website. So log base 2 of 6 equals 2.5, right? So here, that would equals ceiling of 2.5 plus 1, and that would equals the ceiling of 2.5, we explained it before, is 3. 3 plus 1 equals 4. So I need at least 4 digits to represent 5 in any 2's complement binary system. And to verify that, 1, 2, 4, 8, yes, that's how you write positive 5 in 2's complement binary notation. If you have only 3 up to here, right, if you have only 3 digits, you cannot really represent 5. And that's what I mean by length determination. You use these two equations, you use them to, let me write it down, use these equations to determine the minimum number of bits needed to represent a number in 2's complement, in 2's complement notation. So length determination gives you these two equations here. These two equations you can use and then substitute for x to get the length, or how many bits are needed to represent the minimum number of bits that are needed to represent any positive or negative number. And I encourage you to to work with these two equations here, because it's just going to make your life easier. You will not find them in many books, because actually I came up with them. Thank you guys for watching this, and I'll see you in the following tutorial.